Hey, P Statistics. Welcome to Chapter 9. This is the other big one. We just finished up confidence intervals. Now we're going on to significance tests. So 9.1, we're going to look at the basics of significance tests, just trying to get an understanding of what we'll be doing before we get really down into it. So by the end of this section, you should be able to state appropriate hypothesis for a significance test about a population parameter. You should be able to interpret a p-value in context. You should be able to make an appropriate conclusion for a significance test and interpret a type 1 and type 2 error in context, give a consequence of each in a given setting. All right, so confidence intervals are one of the two most common methods of statistical inference. So we've done the confidence intervals. The second common method of inference is called a significance test. This allows us to weigh the evidence in favor or against a particular claim. Truth be told, I think significance tests actually take the prize for most popular, though there's some debate about whether or not people probably should be doing more confidence intervals, but a lot of people like the kind of the finality of a significance test, the conclusion that we draw. So a significance test, or we also call them hypothesis tests because we will be writing out these hypotheses, is a formal procedure for using observed data to decide between two competing claims called hypotheses. The claims are usually statements about a parameter like the population proportion P and the mean mu. We will focus heavily on those two, though technically there are lots of different significance tests you can do for population parameters, and we will do a little bit more. So the claim that we weigh evidence against in a significance test is called the null hypothesis, or H naught. H sub 0, we could pronounce that H naught as like N-A-U-G-H-T if you were going to spell that. So that is the null hypothesis. And then the claim that we're trying to find evidence for is this alternative hypothesis, H sub A. And so we'll need to write those out when we're doing these problems, and you'll be expected to write out your null hypothesis and your alternative hypothesis. So we're weighing evidence against this, trying to find evidence of that. And when we say try, that means like statistically we're trying. It isn't always necessarily a good thing, as I've said in kind of other situations before. So in this case, an example of this, a free throw shooter claims that his long run proportion of made free throws is point P equals 0.8, but we suspect the player is exaggerating. So in this case, we're going to perform a significance test of this based on a sample of data. So we're still doing inference. We're using our statistic to draw conclusions about a parameter. And so our null hypothesis is kind of an equal to hypothesis. It's a statement of no difference. And so that's how we start out with. And then the alternative hypothesis is kind of what we're trying to find evidence for. So we need to... the burden of proof is on showing that it's less than that, and so that's what we're trying to show with this, that it's less than 80%. But as we'll see, and we'll deal a lot with this, just because you get a p-hat slightly less than 80% isn't enough to prove this. We need to think about sampling variability and what would actually constitute proving this alternative hypothesis. So the alternative hypothesis is one-sided if it states that parameter is greater than the null value, or if it states the parameter is less than. So you can have a greater than or less than inequality. Those are considered one-sided hypothesis tests or significance tests. And then two-sided is if we just say that it's different from and not equal to. So we always will have an inequality. So here's my either greater than or less than for my null hypothesis equals 0.8. The alternative is that it's less than or greater than. Those are considered one-sided tests. We're just testing a single direction. Versus you can also run a two-sided test where we're just saying it's different from, it's not equal to. And so we'd say a statistic in either direction that's significantly far away would lead us to drawing a conclusion that the alternative hypothesis is true. But this way we're testing specifically in a direction. So one- and two-sided tests. So example problem, at the Hawaii Pineapple Company, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wondered if this change will affect the mean weight of pineapples grown in the field this year. State the appropriate hypotheses for performing a significance test, but be sure to define find the parameter of interest. So we're going to write a H naught, our null hypothesis, which is our no change, that nothing is different. All right, so it's always an equal to. Our null hypothesis is always an equal to sign, and then our alternative will be different. So so the mean was 31. We changed some things. Is it still 31? And so the null hypothesis will be that it equals 31. The alternative can be a little trickier. Is it the one-sided? Is it greater than? Is it less than? So we have to read into the problem and think and specifically answer the question they're looking for. So they wonder if this change will affect the mean weight of pineapples grown this year. So they're not actually speculating that it's going a certain direction. They would have to say, though, like, they expect it to increase. Is there evidence that it increased? That would be a one-sided. This one is just saying, did this affect it? Is it different? And so this is why we will end up with a null hypothesis where the mean is the same, and alternative where it's different. Did it affect things? And then we need to define that parameter, and this is just like last unit where we say mu is the true mean weight of all pineapples grown in the field this year. So, caution, the hypothesis should express the belief or suspicion we have before we see the data. So you should not wait until after you see your data to then draw your alternative hypothesis. Your alternative hypothesis needs to be set in advance. Do you think, were we testing greater than, are we testing less than, or are we doing a two-tailed test or a not equal to? Because if you wait until afterward, you'll always just do a one-tailed test, and that may be inappropriate, and there's some debate about that. And yeah, always should be decided in advance. State your hypotheses beforehand. Hypotheses always refer to a population, not a sample. So we're always talking about parameters when we say our hypothesis. So be sure to H naught and HA in terms of population parameters. It is never correct to write a hypothesis about a statistic like p hat is 0.8 or x bar is 31. So we'll never write it that way. All right, so the similar example, a player who claimed to make 80% of his free throws made only 32 out of 50, which is 64%, in a random sample of 53 throws. So what we can say is this is evidence against the null hypothesis that p equals 0.8, and it is in favor of the alternative hypothesis. He did do less than 8%, but is this evidence convincing? And that's the big thing that we want to think about in statistics is just because the number's lower, realize there's sampling variability. Is this just chance that we got something that low? So we're going to think about our sampling distribution a lot in this chapter. So in other words, how likely is it for an 80% free throw shooter to make 64% or less by chance alone in a random sample of 50 attempts? And so what we see here is a simulated set. So they did 400 sets of 50 shots. In those, they observed that there were only 3 sets that made less than or equal to the 0.64. So we don't find the probability of exactly that number because any specific outcome is going to be pretty unlikely. We find something that extreme, so that low. And so 3 out of our 50, that's pretty unlikely. And so that 6% chance, we'll end up referring to that as the p-value. That's pretty unlikely, and so we might be convinced based on that if this person really is an 80% free throw shooter, that's really unlikely, and so might reject that claim of being an 80% free throw shooter. So a p-value of a test is the probability of getting evidence for the alternative hypothesis, HA, as strong or stronger than the observed evidence when the null hypothesis is true. So in this case, our alternative hypothesis was less than, and so we went less than. If it was a not equal to, a two-tailed test, we'll actually have to go in both directions, saying, like, what's the probability I would get something that far away from? Or if it was greater than, you'd say, what's the probability getting something that high? So in this case, our p-value is that 3 out of, is this 400? Yeah, 400 sets. So not 50, yeah. So it's much less than the 6% I mentioned last there. So it's a 0.0075, and so that is very convincing evidence. So we'll show you how to calculate p-values later, and so you can actually do this instead of with simulation. We'll do this mathematically, and I bet you could probably even mostly guess kind of how this is done using sampling distributions. But we're just going to focus on interpreting, getting the big ideas in this section. All right, so another example of dealing with p-values. Calcium is a vital nutrient for healthy bones and teeth. The National Institute of Health, NIH, recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decide to perform a test of mu equals 1300 versus mu is less than 1300, where mu is the true mean daily calcium intake in the population of teenagers. They ask a random sample of 20 teens to record the food and drink consumption for a day. The researchers then compute the calcium intake for each student. Data analysis reveals an X-bar of 1,198 and a standard deviation of that. Researchers performed a significance test and obtained a p-value of 0.1404. So they took a lot of the work out of this for us. They already give us the p-value. So, but notice that, yeah, this X-bar is below 1300. And so there is some evidence. Is it convincing evidence? And so that's what we're going to look at there with this p-value. They've done some math to see, what is that? So explain what it would mean for the null hypothesis to be true in this setting. So we're going to do this here. If the null hypothesis is true, then the mean daily calcium intake in the population of teenagers is 1,300 milligrams, and maybe this sample just happened by chance. So the second part is interpret that p-value, and that p-value was 0.1404. And so what does that mean? That is the probability of getting a result as extreme as we did. And in this case, it's specifically less than. So this is assuming that the mean daily calcium intake in the teen population is actually 1,300. So if that was the case, and so when you're interpreting p-value, make sure you include that, assuming the null hypothesis is true. Because we may end up rejecting the null hypothesis, but that probability is based on the assumption of the null hypothesis is true. Assuming the null hypothesis is true, there is a 14% chance, a 0.1404 probability of getting a sample mean of 1,198 milligrams or less just by chance in a random sample of 20 teens. So that's actually kind of high, right? We've already kind of mentioned we look at that 5% as statistically significant. This chapter really gets into that. 14%, that happens pretty frequently. So we might not, we don't really have cause to reject it. That is within sampling variability. It could just be we got a bad sample. All right, so then the conclusions that we draw are based on the strength of the evidence in favor of the alternative hypothesis and against the null hypothesis as measured by the p-value. So if we observe the results that are unlikely to occur by chance alone, when the null hypothesis is true, small p-value, in that case, we reject the null hypothesis. So if we get a very unlikely thing, and we're working under the assumption that the null hypothesis is true, and we get something really unlikely, that what we then say is that, okay, maybe that assumption was wrong. We reject that null hypothesis. If the observed result is not unlikely to occur by chance alone, when the null hypothesis is true, for a large p-value, we fail to reject. So if we get something that, that's pretty frequently happens by chance, then we don't reject it. And so right now we're just saying small p-value, large p-value. What is small and large? We'll come back to that. So if the p-value is small, reject then H0 and conclude that there is convincing evidence for the alternative. If the p-value is not that small, we fail to reject the null hypothesis and conclude that there is not evidence for the alternative in context. So you make sure you include that in your decision. So that's your conclusion. So this will actually be part of our state plan do conclude. And so our conclude step will say, because our p-value is really small, we're going to reject the null hypothesis and conclude that there's evidence for the alternative, and then talk about the story, or vice versa. So there's that question. How small does the p-value have to be for us to reject the null hypothesis? So way back when in chapter 4, we suggested that you use a boundary of 5% when determining whether the results are statistically significant. So what this is saying is this is equivalent to saying view a p-value of less than 0.05 as small. So we've kind of just used that rule, and that is a very common rule we say. If something happens less than 5%, that's pretty unlikely. But you might choose other thresholds for what's unlikely. So sometimes it may be preferable to use a boundary value like 1% or 10% when drawing conclusions, if you want to be really sure, or so on. So we've got this other thing we call the significance level, and it gets the symbol alpha. That's the Greek letter alpha. And so it is the value we use as a boundary for deciding whether an observed result is unlikely to happen by chance alone when the null hypothesis is true. So this is kind of like our confidence level. You remember you can choose a confidence level. We can choose a significance level. How certain do we want to be? How small does that probability need to be so that we reject? So this is if the p-value is less than alpha, we say the result is statistically significant at alpha equals whatever that 5% level or 10% level and so on. And then Likewise, this should be stated before the data are produced so that we don't decide afterward, like, oh yeah, let's go with an alpha of 5% or 10% once we see our data. It should be decided in advance, how convinced you want to be, and there's some other things we'll look at eventually that will kind of guide that decision. All right, so one more example problem here. A company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use. On average, the company selects an SRS of 15 deluxe AAA batteries and uses them continuously until completely drained. The sample mean lifetime is 33.93 hours. A significance test is performed using the hypothesis. So the null hypothesis is that it's the same, that it's still 30. The alternative is that it's greater than 30. Usually we'd make that before we get our sample. And so where mu is the true mean lifetime in hours of the deluxe AAA batteries. That's what we're testing for. So we're assuming that they're the same as the 30-hour regular ones, but we want to find evidence that they're greater than. So we'll eventually get into the math of this. This is the do math that we're skipping over for now, but the resulting p-value is 0.0717. What conclusion would you make at the 5% level, the 0.05 level? All right, and so, reframing this. So because that p-value is greater than alpha, because p of 0.0717 is greater than that, we fail to reject. We didn't quite find a result that's unlikely enough for us to be convinced that it's actually greater than 30. That point, we would only get a sample that high 7% of the time, but that's still not quite unlikely enough. We think it could just be chance. We just got a lucky set of batteries that, were greater there. So we fail to reject the null hypothesis. We don't have convincing evidence that the true mean lifetime of the company's deluxe AAA batteries is greater than 30 hours. One thing to note is that we didn't actually prove that it is 30. We just didn't have significant evidence for the alternative. We never actually prove the null hypothesis is true or even accept the null hypothesis. We just failed to find evidence for the alternative. It's really hard to prove equality. It's much easier to prove inequality, that it's greater than something than it's equal to something. So we'll never accept the null. We're only ever going to be able to accept the alternative. If we get some other result, basically we just go on saying, yeah, that's plausibly sampling variability, but maybe not, right? Like the 39 is higher than 30, but it just wasn't enough to be convinced because it's not a result that's so unlikely it couldn't just be a chance. So we never accept the null hypothesis. All right, and then one last tip. So they recommend that you follow two-sentence structure from the example when writing the conclusions for a significance step. So you're going to state, plan, do, conclude. The first sentence should give a decision about the null hypothesis. So about rejecting the null or failing to reject the null based on an explicit comparison of the p-value to the stated significance level. So because p is greater than alpha, we fail to reject. Or because p is less than alpha, we reject the null hypothesis. And then a second sentence should provide a statement about whether or not there's convincing evidence for the alternative in the context of the problem. So because p was less than alpha and we rejected the null, that means we accept the alternative, or vice versa. If p was greater than the null, because p was greater than our alpha level, we failed to reject the null hypothesis, and we failed to find evidence for the alternative hypothesis, and then make sure you include some context there.